Hi everyone, my name is Paddy Healy and this is the fifth webinar in the series brought to you by Exida, and today we're going to be looking at component data requirements for an FMEDA. So basically, yes, within this webinar we're going to look at the key attributes of a component database, and we're going to show examples of several component metrics that you should be looking for in whatever database you decide to use. And of course, this database is the key element, the glue basically behind your FMEDA. So as I said, this is the fifth in the series brought to you by Exida. We're running 3 sessions a day for each of the webinars. They're free to sign up. So yeah, if you haven't already, sign up and tune in. And as I said, they're available back on playback. And I'll just say now, anyone who's looking for the slides of any of the previous webinars, if they email academy@exida.com and reach out there, and you'll get a copy of the slides. So a bit about Exida. The company was founded over 23 years ago by several of the world's top reliability and safety experts. And as you can see, over those 23 years, the company has really grown to be a truly global company. And definitely it's a place where professionals around the world, they come to us looking for guidance and help when it comes to functional safety. There's 3 main facets to the company. We've the engineering tools division, we've the certification and assessment, and the system lifecycle services. Now, the certification and assessment, that's where I do my day job, as it were, doing FMEAs and FMEDAs and certification for customers. Now, the engineering tools division, they have an in-house software development team, and the tools mentioned here, Excellentia and OEMX, are developed in-house, and they're basically tools to streamline the work process. And as I say, we use them in-house, and they're also available. Customers use them across the world. So when you're doing your FMEDA, and obviously this is going to lead us into the component database and what to look for. Obviously for your FMEDA, you need to start with a good FMEA. And in doing that, you're looking at your system, your device, whatever you're going to analyze at the system level. You break it down into sub blocks within that particular device. Some of those blocks may have a further breakdown into more sub blocks or subsystem architecture. For example, you may have a power supply. That's the first level, the first subsystem, but that power supply then may be further broken down into like your power supply for your low logic level, your microcontroller, your microprocessor. You may have an isolated power supply, you may have AC power supply, and so on and so forth. For these blocks, these subsystem architecture blocks, you describe the failure modes and the effect of those failure modes. And once you've reached this step, this then brings you into doing your quantitative FMEDA, because you've reached the component level. And what you do then when you're doing your analysis, you look at each component individually within each block, and you map the failure of that component back to the particular failure mode of the block, the subsystem block that component is in. So for example, here we're looking at a power regulator IC, and from the database we've gotten the particular failure modes and the failure rates and the distribution for this particular component, and we do this for each component as we move through our FMEDA. So the FMEDA must account for all important failure rate variables, and the drivers. There's 2 main drivers of these failure rates. We have the design strength, which is comprised of the physical materials of the component and component design, the product design related to self-heating of the component, the product design related exposure of component to electrical stress, and the product level design related to ambient temperature rise. And the second one is the operational stress, and this is comprised of the average temperature of the environment, the magnitude and frequency of the temperature cycles, and constant use versus periodic power cycles. So it's these 2 stressors, as it were, are the main drivers for our failure rates. But how do we get, or where did it all start with our component database, and where did the failure data come from? So when Exida started looking at using a suitable database for doing FMEDAs, there were two main contenders at the time. We had the Siemens 29500 database and the IEC 62380 database. Now the IEC 62380 was based on fundamental physics with flexible models that accounted for real-world differences in environmental profiles. And the Siemens database also had useful models. However, neither standard had failure modes and failure mode distributions sufficient for FMEDA work. So the conclusion was, building on these, Exida went off and did its own research and added what they found, this information, to develop their own component database. So if you may want to develop your own database, or you may be looking to use a proprietary database, but what do you look for? What are the key requirements for this database? The database needs to provide failure rates for various design profiles and environmental profiles. It also then needs to provide component failure modes and distributions for various design profiles, and again for environmental profiles. One key element is that it needs to provide the useful life for both design profiles and environmental profiles. There's no point in picking a component that has a useful life of maybe 3 years when you're looking to design a product that you would hope to be up and running in use for 10 years, let's say. So you've straight away you've a weak link in your chain. But by having a good database and having useful life data enables you to straight away decide, will this component be the downfall of our particular product. Within the database then, another requirement is to look at the impact of integrated circuit soft error rates. So again, depending on the design and the application of your product, what altitude this product is going to be used at, and obviously then with things like smaller gate sizes, larger VLSI components, altitude is an impact. So you need your database to be able to have the information there for that type of error rate. The data also needs to be calibrated and validated against field failure data to ensure accuracy. And what I mean by this is that it's okay having a database, but it can't be stagnant. You can't have it just with your failure rates and in 5 years' time the same failure rates are sitting there. You need to be looking and comparing to real-world field failure data, looking at the metrics from there, and then feeding that back into your database to see, do you need to update your components within the database. And then akin to that, data needs to be updated on a regular basis to keep up with changes in technology. As I say, component manufacturers are coming out with newer microcontrollers, microprocessors with various cores. You now have 8-core or 4-core, quad-core microcontrollers, 3D chips as well. So there's various different new technologies coming out. So your database needs to keep up with the changes in technology. And then finally, it needs to contain the data for all the components used in your product design. This is a key element. So if we look at the kind of a basic layout for a database and where the information is, if you can see up here, we have our design profiles. So we're looking at an example here of a silicon carbide transistor, FET, and these are the various different design profiles from 20 degrees junction temperature up to 100 degrees. So what your database then needs to incorporate is that it provides the failure rates for these design profiles and also the failure rates for the various operating environments that this particular component may be in. And this is a key element to look for in your database. Moving on from that then, what we also need to look for then in a database is that it provides component failure modes and distributions for design profiles. So again, looking at our design profiles, which continue down, these are our failure modes, specific obviously to the silicon carbide transistor. And these failure modes change accordingly depending on which particular component you're using. And then that it provides the component failure modes and distributions for these various different environmental profiles. Just to give you an indication, the environmental profiles are something that allows us to basically, if you have a device that you're designing that's going to be used maybe in subsea, high altitude, standard cabinet mount, whatever it happens to be, these different profiles are indicators for those different types of environments, and also the failure rate then changes accordingly. And then, as I said, what's very, very important is the useful life of your component across the various different design profiles. As you can see here, if you're running this particular component at a very high temperature, 100-degree junction temperature, profile 5, which is a high temperature environment as well, you can see that the useful life is only 10 years compared to 20 years for some of the lower temperatures and the less extreme environmental profiles. So yes, the next thing we need to look for is that the data includes the impact of soft integrated circuit soft error rates. And as you can see here, this was an update done to the database where we incorporated the soft error rates into various different failure modes of the microcontroller core element within the database. Next then, as I said, we need to make sure that the data in our database for the components is calibrated. To produce realistic results, the FMEDA component database must be calibrated and validated with field failure data from end users in a similar environment or application. So generally what we do is, after we do our FMEDA, we get a predicted failure rate for the device. This then over time is compared to field failure data sources such as end user studies, SILSTAT or OREDA. And if we find that our predicted is possibly less than the estimated, there's an issue there, there's an error, because our results are probably overly optimistic. And normally in that situation then an investigation is carried out to see what the discrepancy is. And normally one of these three outcomes, where we either have to introduce a new failure mode for the particular component, we might have to update a component within the analysis, or we develop a new component and put that into our component database. And just to give you an example where this might happen, a customer a few years ago came to Exida. An FMEDA was done and the results were a lot less than what they were experiencing in the field. And as it turned out, there was a particular pressure sensor in the device that in the component database that we were using had a shielded membrane that was protecting the pressure sensor. However, the one that was being used in the field had no such thing. So from that then, a new component was added to the component database. So looking at another example here, Exida, this FMEDA results from 35 different pressure transmitter designs were compared with industry data, OREDA, and end user field failure data with Dow. So we plugged in the average from our results, as you can see here on the graph. We compared it to the two field failure results, and as you can see, the result of that was the FMEDA average results based on our calibrated CRD are very close or somewhat pessimistic, slightly higher failure rate compared to the field failure data. So when it comes to safety, it's better to err on the side of caution and be a bit more pessimistic. So number 9 on our list was the data needs to be updated on a regular basis to keep up with changes in technology. As I said, microcontrollers are in a constant state of flux. New devices been constantly added with different features and subcomponents, so the database needs to keep up with them accordingly. And then lastly, it needs to provide the data for all the components used in your design. It's no point in looking at your design and realizing that the database has a single resistor, and that resistor is meant to encompass all possible situations, whether it's high current, low current, so on and so forth, or maybe you have a memory chip with a single capacity and there's no way to possibly change the the size of the RAM you're using. So yeah, your database needs to provide data for all components used in the design, and not just for electrical, also for mechanical components. Because nowadays, obviously, devices are being developed that have both an electrical and mechanical element to them. So your database, if possible, needs to incorporate this information as well. So when you're building a component database, where's the best place to start in looking for the information? So as I said, when Exida were starting their component database, the main source of information they pulled on was the IEC 62380 and the Siemens 29500 databases. But other areas that were key to pulling in the information that went into the database was gathering field failure data from target applications, meeting with component manufacturers, and then also technical papers and component books. Unfortunately, when it came to the mechanical database, it was a standing start. There was no basic database that could be built upon. So the main source of information for the mechanical side was gathering field failure data from target applications, and then also obviously meeting with component manufacturers and looking up technical papers. So just to recap, these are the 10 main requirements to look for when developing a component database, and these really are key and allow you to have the most accurate possible database that you possibly can. As we have said throughout this webinar, an FMEDA can be done whether you're using a spreadsheet or you're using a commercial tool. It makes no difference, but here are some of the key features to look for when you're going to use a particular tool or a spreadsheet. I include that in when I say a particular tool. These are the key features to look for. The only thing I will say is, obviously with a spreadsheet versus a commercial tool, there's probably a higher amount of work that needs to go into to get you to a point where you can just start inputting your data and actually doing your FMEDA. As I said, the tool that is developed at Exida and the one that we use is a suite called OEMX, and this allows us to go from all the way from our requirements, gathering our requirements for a particular analysis, through to our FMEA, through to our FMEDA. And as I say, the key or the core thing behind the FMEDA is the component reliability database. So just to conclude today, an FMEDA result is only as good as the component database. Component failure rates vary with design strength, design stress, and environmental stress. The useful data also varies with strength and stress and should be part of any component database. And then finally, a component database must be updated frequently, and that would be up to you depending on what you see as being most suitable. But obviously technology may be the main driver in how often your database is updated. So just to remind everyone, these are the 8 webinars that we have run and are running in this series. And as I said, if you haven't already signed up, please sign up. They all do work well together as a complete set, starting from what is an FMEDA all the way through to using a commercial tool to do an FMEDA. So I'd like to thank everyone for your time this afternoon. Hopefully you found this informative. And if you have any questions, as I say, I'll just remind everyone, if you're looking for the slides for these webinars, if you reach out to academy@exida.com, and yeah, we'll be able to help you there. So I'll open the floor to any questions that people may have.